Okay, welcome to the staff meeting. We're going to talk about the second tutorial in Physics 207. I'm just going to share my camera. In this tutorial, we're going to look at what happens when a pulse, an incident pulse, reaches a boundary between two springs, a spring that is fast and a spring that is slow. Now, again, some of your students may never have, worried about this problem. They may never have even thought this was a problem worth considering, but this crops up quite a bit. Whenever there's a discontinuity between the speed at which waves propagate, there's always going to be, at the boundary, there's always going to be part of that wave that goes through to the second medium. We call that the transmitted pulse, and part that is reflected back into the original medium. We call that the reflected pulse, of course. And because this happens in so many different situations, it's worth understanding. Now, again, we're going to have pictures that came from that PSSC textbook from the 1960s. They're kind of primitive, but they were the ones that Lillian felt most comfortable with. So that's what we're stuck with. If we look at this set of photographs here, and these are taken at equal time intervals, what we see is that we start with an original pulse that is wide, and it travels to the right and interacts with this boundary right here between the two springs. And you see that when it interacts right here, it splits. The original pulse dies and two pulses are born in its place. We have the reflected pulse here that is then going to go back to the left, and the transmitted pulse here that is going to continue on into the new spring. And what we notice is that the original pulse, when it bounces back, flips. It was on top and now it's on the bottom. And this should remind us of what we saw last week in tutorial when a pulse meets a fixed end. So let's go through and answer some of these questions here. Describe what happens after the pulse reaches the boundary between the springs. We just said it splits into a transmitted and a reflected. Pulse. Pulses, I guess it should say. Compare the widths of the incident and transmitted pulse. Okay, so the width of the incident is much greater than the width of the transmitted. Okay. In part B, we're asked about the speed of the pulse in one spring compared to the speed of the pulse in the other spring. And we're asked to make this comparison in two different ways. The first way, we're going to use the information contained in two or more snapshots. So if I look at, say, snapshot 1 to snapshot 4, you see that pulse has moved, I don't know, like 40% of the width of the picture. And yet if we come down and look at the transmitted pulse, say from 4 to 10, the same time interval, it hasn't moved very far from 7 to 10, it hasn't moved very far at all. Okay, so if we use the information contained in only one single snapshot, like 8, here we've got to use an extra piece of information. And that is that both of these pulses were born at the same time, at the same place, right there at that boundary. I like to talk about them as twins. They were both born at midnight at the same hospital, and they went scurrying in their merry way, this one to the right, this one to the left. And in the time that it took to take this picture, this transmitted pulse has only gotten a little bit away from the boundary, from the hospital, whereas its twin has traveled quite a distance. So this is going to be the fast spring on the left and the slow spring on the right. Now, we remember from class that the speed of pulses on a spring or string is given by the tension divided by the mass density and then the square root of that ratio. And that mass density is just the mass of the spring divided by the length of the spring. Well, the tension, and you can see why I wrote out the word tension there. We use T for so many things, especially when we're dealing with temperature at the same time. The tension in the left spring has to equal the tension in the right spring. Well, there's two ways that you can argue this. One is just a direct appeal to Newton's third law. The left spring is pulling on the right spring, and the right spring is pulling on the left spring, and by third law, they have to pull on each other the same. If students have a hard time with the third law, you can appeal to the second law. Imagine connecting those springs with a ring, bring in a third object, and let that ring be one of those massless objects, one of those idealized, only can buy it in the basement of the physics building sort of objects. And then if I look at the poles on that ring, if it's massless, by Newton's second law, it has to have zero net force. And the only forces acting on it are the two tensions, the tension in the left spring pulling it to the left and the tension in the right spring pulling it to the right. And regardless of what acceleration that ring might have, with zero mass, it would have to have a net force of zero. On the other hand, the linear mass density is directly related to the speed at which pulses travel. And we can see from this formula here that the greater the mass density, the smaller the speed. And so that means that the mass density on the left is going to be less than the mass density of the spring on the right. Or we could say the mass density of the fast is less than the mass density of the slow. Okay, is more relevant answer. Okay. Let's go to the second page. I wonder how I get rid of these side things here. Now's not the time to figure out your software. Well, now we're going to look at what happens to the width of a pulse when it goes from one spring to another. We're only going to look at this point at the transmitted pulse as it relates to the incident pulse. And we're going to do that. The technique we're going to use is to send two pulses. And later we're going to think of those two pulses as the start and the finish of a single pulse. But for now, let's just consider them as two separate pulses. And we're going to ignore the reflected pulses and just look at the transmitted pulses from spring X into spring Y. Imagine that you could measure the time interval that starts when the crest of the first pulse reaches point X and ends when the crest of the second pulse reaches that same point. In other words, you stand right here at point X with a stopwatch, and you start the stopwatch when this pulse reaches you, and you end the pulse when that reaches you. And let's say you get, I don't know, 2 seconds. Made that up. Now, imagine that one of your friends stands here and measures the same thing. Starts the time when this pulse reaches point Y and ends when that pulse reaches point Y. And the conclusion that we would like our students to come to is that the two times would be the same. That if I got 2 seconds here, my friend would get 2 seconds there. And we're given a hint here that's very, very useful. And that is, imagine that you actually had two friends, or more surprisingly, that I had two friends. It's hard to imagine. But the other friend is making the same timing at the boundary. Well, I think it's clear that if I measure 2 seconds between these pulses, that my friend at the boundary is going to see them arrive at the boundary 2 seconds apart because they're on the same spring. Now, if they arrive at 2 seconds apart, that means they also leave that boundary 2 seconds apart. And again, they're traveling slower on this second boundary. Remember, these are the two springs from section 1, the first page. So this is the slow, and this is the fast. They're moving slower after they pass through the boundary, but they still left 2 seconds apart. The second one left 2 seconds after the first one. And because they're moving at the same speed, the same slow speed in this spring on the right, they're going to arrive at point Y 2 seconds apart. Okay. Now, what about the distance between the transmitted crests in compared to the incident crests? Well, in that case, the distance between them is going to be, the transmitted crest, the distance is going to be less than. And if I think of a school bus, this is a magic school bus that can expand or contract as needed. It's the night bus. When this school bus hits this, it's going from a fast medium, like a pavement, nice paved road, and a slow medium, like a really rutted dirt road. When the front of the bus reaches this boundary between the fast medium and the slow medium, it slows down. But the back of the bus is still on the fast medium and is still moving quickly. And so this bus, when it finally gets all the way into the slow medium, is now shorter. The first pulse slows down while the second pulse is still speeding up or still moving fast in the left spring. And so it catches up distance-wise. I hope that made sense. Is the time it takes a single incident pulse to pass by point X greater than, less than, or equal to the time it takes a single transmitted pulse to pass point Y? And here's where we can think of these two pulses as the start and finish of a single pulse. And so it would be the same time. And time is the same. Explain how the change in the width of the pulse as it passes from the first spring to the second is a direct consequence of the difference in speed of the two pulses. So the first pulse slows at boundary while following pulse is still moving fast. Okay. In the diagram above, sketch the transmitted pulses showing the widths and spacings of the transmitted pulses relative to the incident pulses. So what we want to show up here are two pulses that are narrower and closer together. Okay, that's page 2. In page 3, we have a picture that shows an incident pulse coming from the slow side and just about to hit the boundary with a spring that is fast. Essentially the same springs that we were looking at in the first page. Now the pulse is approaching the boundary between the springs from the right. After the trailing edge of the incident pulse has reached the boundary, will there be a reflected pulse? Yes, there will be. If so, on which side of the spring will the reflected pulse be located? How will its width compare to the width of the incident pulse? Well, if we use the same reasoning that we did on the second page and think of this single pulse as two pulses, one representing the front of the pulse and one pulse representing the back of the original pulse, those two pulses are going to meet the boundary and reflect back in the same spring at the same speed that the original pulse was moving. And so the timing, because they're in the same spring and they left the boundary at the same time interval that they arrived at the boundary, it's going to have to be the same width. So yes, the transmitted pulse will have same width as the incident. Which side of the spring will the reflected pulse be on? Well, it's going to be on the same side. Okay, on the same side. Now, the reason I say that is that coming into this very light spring, a fast spring is a light spring with small mass density, is like meeting a free end at a boundary. And we found in the tutorial homework last week that when something hits a free boundary, the reflected pulse is on the same side as the incident pulse. Now, what about the transmitted pulse? Well, it's going to be wider than the incident. Now, some of the students are going to want to talk about the amplitude of the respective pulses. There's always three pulses. There's the incident or mother pulse, and then there's the two twins, the transmitted and the reflected. And it turns out that that making predictions about the amplitudes of the pulses is kind of messy. I mean, we can say that the reflected pulse is always going to have a smaller amplitude than the incident pulse because they're on the same spring and some of the energy got transmitted into the other spring. But that's as far as we can go. Giving the amplitude of or predicting the amplitude of the transmitted pulse relative to the incident pulse is complicated. So we're just going to dodge that bullet. Very rarely does a student ask about that question, but if they do, be prepared to brush them off and just tell them it's messy. Okay, in the space below the photograph, make a sketch that shows the shape of the springs at an instant after the incident pulse is completely transmitted. It should illustrate the relative widths of the pulses and the relative distances from the boundary, as well as which side of the springs each pulse is on. So what I would have here is the reflected would be the same width, and it would be going this way. And then here, I would have something of a bigger width going into the new medium, and here's the boundary there. So the transmitted pulse is wider and it's further away from the boundary than the reflected pulse. So maybe the boundary would be over here. Okay. Now, ask a tutorial instructor for the time sequence of photographs that illustrate this situation so that you can check your answer. I have here this drawing, and I will send you a digital copy of it so that you can make your own copies. It's really, this is a Xerox of a Xerox of a Xerox, and so it really isn't very clean, but you see in this frame here that the reflected pulse is the same width as the incident, and the transmitted is wider, and it's further away from the boundary. The boundary's right there. So I will include that in the files that are sent to you. Okay, let's build a model for reflection at a boundary. Let's worry about the reflected pulse. We have observed that reflection occurs when a pulse reaches the boundary between two springs, that is, where there is an abrupt change in medium. we would like to be able to predict whether the boundary will act more like a fixed end or more like a free end. In the situation illustrated in section 1 on the first page, are the incident and reflected pulses on the same side of the spring, or are they in the opposite side of the spring? They're on opposite sides. On the basis of this observation, does it appear that the reflection at the boundary is more like reflection from a fixed end or a free end? A fixed end. That's easy enough. Now, which of the following quantities are different on the two sides of the boundary? The tension is the same. The linear mass density is different. And the wave speed is different. Which of the above quantities could you use to predict whether the boundary will act more like a fixed end or more like a free end? Well, the ones that are different. Either the speed or the linear mass density could be used to predict whether it acts like a fixed end or a free end. The linear mass density is the more intuitive one. When you go from a light spring to a heavy spring, it's like meeting a fixed tied to the wall sort of situation. That heavy spring is hard to move. If you go in the other way, it's very easy to move the light spring. So, for example, if I had, it says we should consider limiting cases. Okay, so this would be fishing line, and this would be heavy chain. Okay, a pulse coming on the fishing line is going to see that as a fixed end and is going to reflect back opposite, whereas a pulse coming this way would see that fishing line as a free end and would bounce back that way. Okay. Describe how you could predict whether the reflected pulse would be on the same side of the spring as the incident pulse or whether it will be on the opposite side. So if we go fast to slow, or this would be light to heavy, it would be a fixed end. And if we go slow to fast or heavy to light, it'd be like a free end. Describe how you could predict whether the transmitted pulse will be on the same side of the spring as the incident pulse or whether it will be on the opposite side. This is really easy. Transmitted pulse is always on same side as incident pulse. And the key word there being always. Imagine that a pulse on a spring is approaching a boundary. Would the boundary act more like a fixed end or more like a free end if the spring is connected to a very massive chain? That'd be a fixed end. And a light fishing line would be a free end. Okay, that's the tutorial. It's very, very straightforward. It doesn't take very long. And I wish you all the best of luck. I'm going to end the recording here.